So what does Courcelle theorem prove? If a graph property can be expressed in this logic, then for every fixed w greater than or equal to 1, there is a linear time algorithm for testing this property on graphs having tree width at most w. Right? But here it is like f of w, okay, times n. But this f of w is like very bad expression, like it could be double, triple, exponential, like the one which directly comes from this Courcelle theorem could be used as a classification theorem in the sense that, oh, it will tell us that, okay, this definitely means that the problem is fixed parameter tractable parameterized by tree width. Okay. So now that we know that fact, we will try to apply a direct dynamic programming algorithm to design algorithm which could be way more efficient. So there is something hidden here. So what is hidden? Hidden is size of the formula. Okay. So now look at this formula, right? Look at this formula. What is the size of this formula? So this is like a constant length formula because you just you just count the symbols which you use, number of symbols. That's it. Okay. So if the formula has a constant length, okay, if the formula has a constant length, then this is like hidden, so you don't care. Okay. So what does it mean? If we can express a property in EMSO, then we immediately get that testing this property is FPT parameterized by tree width. So now we can ask ourselves a problem: can we express 3 coloring and Hamiltonian cycle in this? Okay. So look at the 3 coloring. So what is the 3 coloring? So what are we saying? That exists C1, C2, C3. So this is basically says that, okay, here is C1, C2, C3. It's a subset of V. And now what are we saying? For every V in V, so V either belongs to C1 or V belongs to C2 or V belongs to C3. Okay. So every vertex, so this tells us that the first 3 thing tells us the existence of this subset. Third thing tells us every V appears in some partition, maybe in more than one. Okay. And what will you know? For all V in V, okay, for all V in V, adjacent of UV, look, so now look at any UV. Suppose they are adjacent, means there is an edge. Then what I want to say? Then both U and V do not appear together. And how do I show this? Oh, U and belongs to C1 and V belongs to C1 does not happen. U belongs to C2 and V belongs to C2 does not happen. U belongs to C2 and V does not belong to C2 does not happen, which implies that any graph G which will satisfy this property has a property that it is 3 colorable because what? So we can find a 3 partition, every vertex appears in one of the parts and each edge is going across. Okay. So that's it. Okay. What about Hamiltonian cycle? So I will not do it, but basically all we are saying that there exists H subset of my edges which is spanning, and for all V in V, degree of V in H is 2. Okay. So I will provide this slides, you can go through, and this is a slightly bigger formula, but what is interesting is that all these formulas length is is constant, like you can just count all these things, okay, which is constant, which implies that all these problems like 3 coloring Hamiltonian cycles are FPT parameterized by tree width. Okay. So there are 2 ways of using Courcelle theorem. The problem can be described by single formula, example 3 coloring or Hamiltonian cycle, or problem. So for those problem can be solved in f of w times n for graphs of tree width at most w, or so that implies the problem is FPT parameterized by tree width of the input graph. But sometime the problem can be described by a formula for each value of the parameter k. So for example, for each k, having a cycle of length exactly k can be expressed as there exists V1 to Vk in V and these are adjacent to each other. That's it. So now notice that if I am looking to find a k length exact cycle, then this problem is FPT parameterized by Fk, the length of the formula, comma W. So then the problem is FPT parameter, like FPT running in time FKW times n for a graphs of tree width. So problem is FPT parameterized by combined parameter K and tree width W. So there are several ways of using this. So sometimes in a problem, the kind of problems we will generally people deal with, so they are able to at least get formulas of this kind, and secondly they are able to reduce the W to as a function of K, so everything will imply that it is a FPT parameterized by that function of K alone. Okay? So there are several ways we could use it, and whichever way we are using it, we have to say that this is FPT parameterized by this. So basically, you should always remember that the Courcelle theorem implies the problem with FPT parameterized by formula length, comma, tree width. So if the formula length is constant, this becomes just W. If the formula length is also important, then you have to represent both formula length and W. So this is how course. Now think about your any favorite problem. Try to write a formula for that. If you are able to write formula in the language described by this, then you know that the problem with FPT parameterized by tree width. So this provided a uniform answer to all the questions which was FPT parameterized by tree width, and this was proved by Courcelle, and this is why it is called Courcelle's theorem. Okay. So let's look at another example, subgraph isomorphism. So you are given a graphs H and G, and we want to find a copy of H in G at subgraph, and parameter is size of the subgraph. So for each H, we can construct a formula phi A that expresses G as a subgraph isomorphic to H, similar to K cycle in the previous, right? So how we wrote, right? There exists V1 to Vk in V, and V1 and V2 are adjacent, V2. So for example, so suppose H is this graph, right? And this graph, then we will say, okay, and suppose I want to, so there exists V1, V2, say V1, V2, V3, V4, so let's call it W1, W2, W3, W4, and W5. So we'll say, okay, there exists V1, V2, V3, V4, V5 in V, and this, okay, so we are thinking of W1 as being V1. So then what is, and what is this? There exists, and what happens? Adjacent V1, V2. Okay. Now adjacent, you just, and you would put all the adjacency conditions, and this is the way you can express that H, there exists a subgraph isomorphic to H, right? By writing down these expressions, and for each of these guys, you like think of some names in their head, some symbol name, and you say, look, whatever the adjacency relation is, you just write here. Okay? Okay, that's it. So what does that imply? That implies that by Courcelle's theorem, subgraph isomorphism can be solved in time f HW times n if G has tree width at most W. Okay, and since there is only a finite number of subgraphs on K vertices, subgraph isomorphism can be solved in time FKWN if H has K vertices and G has tree width at most W. So now you know that subgraph isomorphism is FPT parameterized by combined parameter K and the tree width. Now look, why we are saying combined parameter K and H? Because now the length of the formula here, whatever we are writing, actually depends on K, which is vertex set of H, right? And that is the reason why we wrote down this. Okay. Now we have seen several graph theoretic properties of tree width. We will see some more now. So it is known that some fact. So tree width is at most 2 if and only if graph is a subgraph of something called series parallel graph. Okay. And for every k greater than or equal to 2, tree width of k plus k grid is exactly k. So we have already talked about some of these things in our first week. So some more facts, and we also know that tree width does not increase if we delete edges, delete vertices, or contract edges, and hence we have shown that if f is a minor of G, then the tree width of f is at most the tree width of G. So remember what we said, we have also already defined what is an f is a minor of G. If you can get, how can we get f from G? You start with G prime, which is a subgraph of G, which is basically means you have deleted some edges and vertices, and now you only apply some contraction operation to get f. So, any graph that can be obtained from a particular graph G using this operation is called minor, and we have already proved that if a graph has a minor h, then the tree width of h is at most the tree width of G, and this is why this is also called minor closed properties. Okay. Okay. So, what does this imply? The tree width of k click is k minus 1, and it follows from the fact that for every click k, there is a bag B, right, with k which is contained inside B, right. So, if a graph contains a click of size k, then you know the tree width has to be have at least k minus 1, because you will contain a bag containing all the vertices of a click, and this also we have seen in our first lecture. Okay. And so, but there is another, so what does this provides? So, existence of big click implies tree width is big, but there is another structure which is not as dense as say click, but that existence also provides a existence of what is that called, big grid. So, what is so this is the excluded grid theorem which was proved by Seymour plus Robertson and Seymour in graph minor papers. Okay. What do they prove? If a tree width is large, then G has a k cross k grid as a minor. Okay. So, a large grid minor is a witness that tree width is large. So, if you do not have a small, if you do not have some big grid as a minor, then what you know, its tree width is small. So, notice that this function, so this, let us spend some time on this function. So, this basically was the function, if you look, 2 to the power k square log k. Okay. So, they proved that if the tree width is like 2 to the power big of k square log k, then a graph contains k times k grid as a minor. Okay. But whatever further, but however they proved is that if I have a planar graph, then this is not true. What is, if a planar graph has tree width at least 4k, then it contains k times k grid as a minor. Okay. So, while if on a general graph existence of like you need an exponential lower bound on the tree width to prove an existence of k times k grid as a minor, on planar graph, like if the tree width is like tree width and grid are linearly related, means like if you have a tree width is just 4 power k, it has k times k grid as a minor. So, it was a big open question in the literature on general graph. Can we say that if the tree width of G is more than some k to the power big of 1, then it has k times k grid as a minor? Surprisingly, it was open for long time before Chandra Chukuri and Julia Chuje showed it an upper bound of k to the power some 99 and some log. But after successive paper, now it has been shown that the tree width is even just k polylog in k, then that implies existence of k times k grid as a minor. Okay. So, it is one of the very important and big theorem in graph theory is that this excluded grid theorem. So, now notice if I can somehow prove that, oh, look at the graph does not have a k times k grid as a minor. What does it imply? The contrapositive of this implies the tree width of the planar graph is at most k, 4k. Similarly, on the general graph, if I say, hey, there is no k times k grid as a minor, which will immediately imply that the tree width is at most k to the power 10, for example. Okay. Okay. So, in fact, you can prove something more that every planar graph with a tree width at least 4k can be contracted. So, not only you can contain k times k grid as a minor, but in fact, you can you can get following kind of grid just by contraction. Okay. So, look, so when we say that grid as a minor, what you say that, look, if a tree width is larger than 4k, then by deleting some edges and contracting, I can get k times k grid as a minor. But imagine that I do not allow you to delete vertices or delete edges, and only thing which you are allowed is contract. Even then we can show that we may not be able to get a grid, but we can get a grid like structure, which you can see here, and it is also called partiality triangulated k times k grid. Okay. So, not only 4k, tree with 4k implies k times k grid as a minor. In fact, it also implies something which we can obtain just from contraction. Okay. So, now we saw there is another relation of tree width on planar graph that exists, that is exploited quite a lot. So, there is a notion of outer planar graph. So, a planar graph is called outer planar if it has a planar embedding where every vertex is on the infinite face. So, just look at this as an infinite face, okay? And it is known that every planar graph has tree width at most 2. Of course, every outer planar graph is series parallel. Okay? So, in fact, what is interesting is that you can come up with the notion of what is called k outer planar, where you first a graph is called k outer planar if it is a planar embedding having at most k layers. So, what do you mean by at most k layers? So, look at the vertices on the top layer, right, that is k. Okay. So, look at all the vertices which are on the outer layer, give them a number k, okay, that is 1. Now, if you delete them, okay, what is left is some other vertices, give them layer 2. So, you can, what is the minimum number of layer that you can do this to achieve, so such that, okay, what you are left with, everything is outer planar, right. So, the minimum number of layers you need to get to an outer planar graph is called k outer planar. So, if you need k layers, so for example, it is a, what we had was a 3 outer planar graph, because we could reach this. Okay. So, we had first, so you delete all the vertices which are on the outer planar layer or infinite layer, you get, after you delete them, you get another set of vertices which are on infinite or which are in the outer face, you delete them, you get another set of vertices which are on the outer face. If that is the only one, then number of times you have to do this is called outerplanarity of the graph. And what is known is that what is known is a very nice relation between outer planar and tree width, which we will exploit it for some of the examples or which we will see in a minute. So, look at some of the applications we have. Okay. So, now let us try to prove that subgraph isomorphism for planar graphs. So, you are given a graph H and G and parameter is k. So, look at the layers of the planar graph as in the definition of k outer planar. Okay. And so, you fix some integer s and 0 to k plus 1. Okay. Now, let us delete every layer Li with I equal to s mod k plus 1. What is the meaning of this? So, you have layer. So, you give them layer number 1, 2, 3, k plus 1. Okay. Then again you call layer 1, 2, 3, k plus 1. Again you call 1, 2, 3, k plus 1. So, I say now let us delete all the layers with number 1. Okay. Okay. 1, 1, 1, right. Now, after you have deleted it, right, what you have? Every component of a graph, every component of the graph is completely contained inside this, and every component has at most some k layer. Okay. So, this is what means you fix an integer 0 and you delete all layer with some mod k plus 1. Okay. Okay. What do you know about this? Right. So, whatever you see that you are deleting different things. So, you basically you delete some of these things and you will get all these pieces. Now, what you know that every component is a k outer planar, and it is known that if a planar graph is k outer planar, then the tree width is at most 3k plus 1. Okay. So, if a planar graph G has k outer planarity, then tree width of G is at most 3k plus 1. Now, that is great for us. Why? Because why this is important? So, suppose my H, look at this planar graph H, it has only k vertices. Now, if it has at k vertices, then by pigeonhole principle, one of the layer 1, 2, k plus 1 does not contain its vertices. Am I right? So, if it does not contain, say it does not contain, either it does not contain vertices from layer 1 or it does not contain vertices from layer 2 and so on, like it does not contain vertices with, say, so we, what did we did? 1, 2, 3 k plus 1, 1, 2, 3 k plus 1, 1, 2, and this is why we call, so we made like, so what was this? L1 is like all 1 layers, like 1 from each, 1 2 k plus 1 the first one, then next 1 2 k plus first layer. So, and similarly L2. Similarly, now what you know that because our graph only had k vertices, one of the layers it does not contain any vertices. So, if we have guessed the correct layer, then what you know, after I have deleted that guessed layer, then every connected component has at most k layers, and hence its tree width is at most 3k. So, now we can apply our f of k 3k plus 1 algorithm of subgraph isomorphism and solve my problem, right. Now, if any of the if for any of the call of subgraph isomorphism we succeed in finding this subgraph, then we are very happy. Otherwise, what we know about this? We know that there is no subgraph, because if there was a subgraph of this H, then at least deleting one of these layers, okay, will preserve that subgraph, and we would have found this using this dynamic programming. So, this is why it is called, in some sense, this is a very famous strategy which is used in polynomial time approximation scheme. We will see its application in a few minutes also, but you notice, right, this is like you divide, so it's like you divided your layers into 1 2 3 k plus 1, 1 2 3 k plus 1, right. So, it's like 1 2 3 k plus 1, then 1 2 3, and then you say, look, imagine that it does not contain vertices from layer 1. So, then it will contain only here, right, and I know, and the tree width of a graph is basically maximum of tree width of connected components, and each connected component has layers at most k. So, the tree width of each connected component is at most 3k plus 1, which implies the tree width of the whole graph is at most 3k plus 1, and you will be able to find this pattern. Okay? I hope this is clear. Okay. So, we do this for every s at most between this, and for at least one value of s, we do not delete any of the k vertices of solution, which will imply that we will find a copy of H in G if there is one. Okay? Okay. 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 Now, let us detour to the approximation. Okay. So, what is a C approximation algorithm for a maximization problem? Is polynomial time algorithm that finds a solution of cost at least op divided by C. And a C approximation for minimization problem is a polynomial time algorithm that will find you a solution of cost at most op times C. And there are several approximation algorithms for NP hard problems, like for vertex cover they have factor 2 approximation, max 3 by set 3 set 8 by 7 approximation, metric TSP 3 by 2 approximation, and so on and so forth. Okay. For some problems we have a lower bound, that is there is no 2 minus epsilon approximation for vertex cover or 8 by 7 minus epsilon approximation for max 3 set, of course under suitable complexity assumption. For some other problems, arbitrarily good approximation of them is possible. So, for any c greater than or equal to 1, say c 1.001, there is a polynomial time approximation, polynomial time C approximation algorithm. Okay. And there is a notion of what is called polynomial time approximation scheme. Okay. So, what happens in polynomial time approximation scheme for a problem P? So, it takes an instance of problem P and it takes a parameter epsilon. Okay. And it will always find you a 1 plus epsilon approximate solution, but the running time is polynomial in n for every fixed epsilon greater than or equal to 0. So, what could be the running time? The running time could be 2 to the power 1 over epsilon times n, or maybe some n to the power 1 over epsilon, or maybe n over epsilon to the power whole square, and n to the power 1 by epsilon square, right. So, So, if you think of this, it's like we are trying to think of a beta says as whether it is an FPT or XP algorithm in the parameter 1 over epsilon, right. So, you can do all kind of things here. Okay. Some classical problems that have betas like independent set for planar graphs, TSP in the Euclidean planes, Strainer tree in planar graph, knapsack, and so on and so forth. Okay. So, let us look at this Bater shifting strategy for epetas. Okay. So, there is a 2 to the power 1 over epsilon n times betas for independent set for planar graphs. So, you set d equal to 1 over epsilon, okay. And now, as we did it for this subgraph isomorphism, you look at your planar graph and you draw them outer planarity layer, okay. And as always, what is this Li? Those I who leaves S when you divide by d. So, all those layers who is like mod d, okay. So, now, so the result, so now if you delete any layer, what is the property of this graph? It is a d outer planar, and hence its tree width is at most 3d plus 1 order. So, using the time 2 to the power w times n, there exists an independent set, for independent set, we can solve this problem in time 2 to the power big of 1 over epsilon times n. So, what we did? So, based on 1 over epsilon, we fixed a number d and we deleted some layers, okay, like, okay. And on each we solve the problem, and what are we going to output? So, we do this for every s between 0 and 2, and we will output the layer with respect to which the weight of the independent set is maximized. What do you know about? So, look at a pigeonhole principle. What does pigeonhole principle tells us? That look, this is some layer, this is some layer, this is some layer, this is, and these layers are disjoint, right. Now, your independent set vertices are distributed among them, right. Now, when I say layers, this is like some set of layers L1, L2 and LS or LD, right. Now, look at the independent set vertices. By pigeonhole principle, at least one layer will contain at most 1 over d fraction of this, right. So, at most, so you would have returned, suppose the solution had size weight w. So, what will you return? W minus, at least solution of size, you will return w minus epsilon yeah. Yeah, so if you do this by pigeonhole principle, you will be able to show that you only lose d over epsilon, you lose 1 over epsilon fraction, or not even 1 over epsilon fraction of the total weight, and you are able, and that if you do maths, you will get 1 plus epsilon approximation solution. So, I mean, I leave this maths to you, okay. But the idea is that if the total weight was w for max weight independent set, there is you will lose how much? W, there is a layer which contains at most w by d. So, you will definitely be returning a solution of weight this, and if you do maths, this will come 1 plus epsilon approximate solution, okay. Okay. So, now let us go back to FPT algorithm. Okay. So, this we have already discussed when we were talking about the applications. Why we care about tree width in parameterized algorithms. So, I told you that look, using this DFS tree, either we can find a long path or long cycle, or we can compute a tree decomposition. Okay. Now, if we can compute a tree decomposition, we can apply again Courcelle's theorem, and otherwise the graph has tree width at most k minus 2. We have already done this, and then once the graph has bounded tree width, we did not do anything in our first peak lecture, but now we know Courcelle's theorem. We can write down this formula, and using this we can show that finding a cycle of length at least k in a graph is FPT parameterized by k. Because why? Because the running time will be f of w comma times n, but w is here like where k is a length of the formula, which is k, and w is also become k. So, you are done. Okay. So, yeah, so we have already seen this, so we will I will leave this out. But this is the one thing which we have not talked about, and let's spend next 10-15 minutes on what is called bidimensionality. So up until now we have been designing an algorithm with running times either c power k or k power k, but you would have seen an algorithm via chromatic coding, okay, where we design an algorithm with running time 2 to the power little of k. What is the meaning of little of k? Is basically something like 2 to the power big O of root k log 1 over k, or maybe 2 to the power big O of k 2/3, but not like something little o of k. Okay. So, for example, 2 to the power big O of k by log k is also 2 to the power little of k. And it is a very powerful framework to obtain efficient algorithm on planar graphs for this. Okay. So, let chi_j be some graph invariant, that is an integer associated with each graph, and some typical example: maximum independent set size, minimum vertex cover size, length of longest path, minimum dominating set, minimum feedback vertex set. And our question is, given g and k, we want to decide whether x of g is less than equal to k or x of g is greater than equal to k. Meaning, I want to say, is the vertex cover at most k, is feedback vertex set at most k, is dominating set at most k, is longest path, is there just a path of length at least k, is the independent set of size at least k. And for many of these natural graph problems or graph invariants, we can actually design an algorithm with running time 2 to the power big O of root k polygon, or if nothing, then we can definitely get this. Okay. And we will see how we will be able to do this. Okay. So, our observation is very simple. Let us look at the vertex cover. I say, if the tree with a planar graph G is at least 4 root k, okay, fine, if it is at least 4 root k. And how can we check this? How can we check this? We already designed an algorithm that given c an integer k, it runs in time some c power t, right, t, and test whether the tree width is at least this much or not. So, for even a planar graph G, and we want to test whether tree width is at least 4 root k, so this we can do in 2 to the power big O of root k times some n to the power big O, we can check. Okay. If the tree width is large, what can we say? Well, it contains, of course, you need to be a little clear. You want to say tree width is at least 4 root 2k or something or not. Okay. Okay. So, what happens? So, it contains a root 2k times root 2k grid minor. Now, if look at this as a grid as a minor. So, now look at these red edges. What are they? They are matching edges. So, any vertex cover of this grid must contain at least one vertex of this matching edge. So, if the number of matching edges is strictly larger than k, then so what is this? So, look at this. This is like you will at least need root 2k vertices from here, and the root 2k times root 2k, which is and divided by 2, because so like just so root 2k times root 2k is like 2k divided by 2, which is like k. So, if you have a slightly larger grid, then you know that this minor itself needs k vertices. So, of course, the whole original graph needs more than k vertices to in the vertex cover. So, you can say no. Okay. Okay. So, or the vertex cover of size grid is at least k times k, at least k in the grid, which implies vertex cover size at least. So, how do we use this observation to design? You set w equal to 4 root k. We use the 4 approximation tree decomposition, 4 approximate tree decomposition 2 to the power big O of w. So, it will run in this line. So, if tree width is at least w, we answer vertex cover is greater than or equal to k, done. Otherwise, you get a tree decomposition of width 4 w, then you solve your problem in time 2 to the power big w. So, you are done. So, basically, what is this problem all about? Like, okay, I check the tree width of this graph. If the tree width is large, I say no, there is no vertex cover, or we have found a small tree decomposition. Now, I apply my dynamic programming algorithm and we have solved the problem. But this is nothing about vertex cover that we use. Only thing we used is that, oh, what is the solution size on the grid? Okay. Okay. So, So, that defines a notion of what is called minor bidimensional. If what is minor bidimensional? So, the parameter, like the solution size does not increase on the minor, and if you have a k times k grid, then the solution is at least C times k square. We already saw for vertex cover. What about feedback vertex set? For feedback vertex set, okay, so this is for the vertex cover. Now look at the longest path. So look at this. This is like a big path, right? So if you have a more than some, so it means if you have a k times k grid, then the length of the longest path is of order k square. The problem is minor bidimensional, and on minor and length of the longest path cannot increase like on the minors. So it is minor bidimensional, and it is like first property holds, and secondly solution size on the grid is like order k square. So this is a minor bidimensional property. Okay. What about feedback vertex set? Again, feedback vertex set does not increase on minors, and if you look at k times k grid, then you can get these vertex disjoint cycles of like order k square vertex disjoint cycle, which implies you at least need order k square vertices to intersect all these cycles, which implies feedback vertex set is minor bidimensional. Now if you have, so then what does this tells us? So for minor bidimensionality, this is the algorithm we can get. So we can answer chi j greater than or equal to k for minor bidimensional following way. You set appropriate c root k as w, you apply a factor 4 approximation, and if the tree width is large, you say answer, you know that xg is at least k. So for maximization problem you might be able to say this is a yes instance. For minimization problem, you might be able to say it's a no instance. Otherwise, you have got a small tree decomposition, and then either this running time, then you will get such an algorithm. If you had w to the power big of w time algorithm, then you will get such kind of algorithm. So very simple strategy for planar glass. What is this? I check whether my problem is minor bidimensional or not. Then I just need to check whether it had some appropriate c power w or w to the power w algorithm. Depending on that, you know that it has such and such algorithm, and that's it. But there are problems which are not minor bidimensional, like for example dominating set. Now I will give you an example. Look at this. It is a dominating set of size 1. Now let's delete all these edges. Okay. Then what will you get? You will get a path, and now you can check the dominating set is strictly more than 1. One vertex cannot help you or is not sufficient. So this is graph A, this is B. B is a minor of A, but dominating set of B is strictly more than dominating set. So dominating set is not minor bidimensional, right? Because when I take minors, the dominating set size can increase. Okay. So we will fix this problem by allowing only contraction, but not edge or vertex deletion. So we say, look, find dominating set, but what is the property of dominating set? If you contract edges, dominating set will not increase. And these are the problems which are called contraction bidimensional, where the parameter does not change edge, where G prime is only obtained by contraction, not by vertex or edge deletion. Okay. But now we cannot talk about k times k grid, but we will talk about k times k partially triangulated grid. On this partially triangulated grid, the size of your solution should be order k square. Example, minimum dominating set or maximum independent set, because you look at this, right? Look at this, right? Now look at the central vertex. Where are his neighbors? His neighbors are here, here, here. Where are his neighbors? Here. Like, so you have found set of vertices whose close neighborhoods are pairwise disjoint, and if you have found the set of vertices with pairwise disjoint closed neighborhood, that is a lower bound on the dominating set. So what we know that minimum dominating set is and maximum independent set are in fact contraction bidimensional, but they are not minor bidimensional. And look at the maximum independent set, right? Again, you look at the vertices which are so that the neighborhoods are disjoint, then that is a lower bound on the solution size. So, these problems which are closed in the contraction, in the sense that the solution size does not increase when we take the contraction, and the solution is quadratic on partially triangulated grid, then these kind of problems are called contraction bidimensional. But then then the story can be repeated similar to what we did for minor bidimensional, right. So, now you set up again appropriate W, you compute 4 approximate solution, right. If tree width is large, you know this is more than k, otherwise you have a small tree width and you can get dominating set can be actually solved in 3 to the power W. So, you can show that dominating set is sub-exponential. So, even for contraction bidimensional problem, it all if it is a contraction bidimensional problem, then you can immediately get a sub-exponential algorithm. Okay. So, as a summary, our notion of tree width allows us to generalize DP on trees to more general graphs. Standard techniques for designing algorithms on bounded tree width graphs, we saw dynamic programming and Courcelle theorem, and we saw surprising use of tree width in other contexts such as planar graphs and in designing FPT. Okay. So, I think with this I will close our session on tree width. We can talk a lot more things about tree width, but for a course which is as basic as this, I think amount of information, amount of knowledge we have learnt or we have talked or discussed is enough. And if you need more, then please let me know. I will give you some more pointers, as well as I'll give you some more pointers. Thank you.